Today, we're doing something pretty cool. We're going to pull back the carbon fiber curtain and really dissect one of the most advanced machines on the entire planet, a modern Formula One car.
So let's just kick things off with a single number that says it all, over 1,000 horsepower. It's a staggering amount of power for sure, but honestly, that's just scratching the surface of this story.
Because what goes fast must slow down, right? And here, it's just brutal. F1 drivers pull 5 Gs of force every time they brake. Now, to give you an idea of what that feels like, it's like your leg suddenly weighs over 200 pounds every single time you stomp on that brake pedal.
And that really gets to the core paradox of driving an F1 car. This quote from the Mercedes team just nails it. It's this constant, insane mix of raw physical power and the most sensitive, delicate touch. You're stamping on a pedal with incredible force, but you're also modulating it with the precision that's just, well, it's superhuman.
So you gotta ask, right? How is any of this even possible? How do you actually engineer a machine that can handle these insane extremes? Well, that's what we're here to do. Let's start dissecting the tech from the fastest R&D lab on the planet. First up, we've got to look at how these cars tame the very air around them. It's all about mastering invisible forces to, and Mrs. Literal, glue the car to the asphalt, especially when they're flying through the corners.
And the magic word here is downforce. You can think of it as the exact opposite of what an airplane wing does. Instead of creating lift to take off, the car's shape is designed to generate a powerful force that pushes it down into the track. We're talking a force that, at top speed, can be more than 5 times the car's own weight. Yeah, that's enough to theoretically drive upside down in a tunnel. But the real game changer is how they make this downforce now. See, for years, it was all about big wings. They worked, but they left this wake of turbulent, dirty air behind them, which made it super hard for other cars to follow closely and race. The big rule change in 2022 brought back something called ground effect. This uses specially shaped tunnels under the car to create a low-pressure zone, basically a vacuum that sucks the car to the track but with a much cleaner wake. And that means better racing. And look, this proves that aero isn't just about the big wings you can see. The suspension is just wildly complex. It's engineered down to the micron to work with the aerodynamics. It's not just holding the car up, it's actively fighting those cornering forces and angling the tires just right to squeeze every last drop of grip out of that downforce. But the aero isn't just sitting there. The drivers can actually control it. You've definitely seen the drag reduction system, DRS, right? That flap on the rear wing pops open on the straights to cut drag and help with overtaking. But for 2026, they're taking it way further. We're talking movable front and rear wings. This will let drivers switch between a high downforce mode for corners and a super slippery low drag mode for straights. It's like having 2 different cars in one. All right, let's move from the car skin to its incredible hybrid heart, the power unit. And this thing is not just an engine. It's a 1,000 horsepower work of art that somehow combines raw, brutal power with an efficiency that will just blow your mind.
So what's actually in this beast? Well, you start with the engine itself, a tiny 1.6-liter V6 turbo. But then the magic happens. You have 2 electric motor generators. The MGU-K grabs energy from braking. And then there's the MGU-H, which does something that sounds like science fiction. It recovers energy from the turbo's waste heat. All that recycled power gets packed into a special battery, just waiting to be unleashed. And the results of all this hybrid tech? I mean, just look at this. It is a complete revolution in efficiency. Back in 2013, before all this, a car burned through 160 kilos of fuel in a race. By 2020, that was down to 100. And the target for 2026? A measly 70 kilograms. They are squeezing way more power out of way less fuel. It's incredible.
So, how does this stack up against, say, its all-electric cousin, Formula E? Well, they're on different missions. Formula E is a pure testbed for road car EV tech, recovering massive amounts of energy just from braking. Formula One, on the other hand, is pioneering this hyper-complex hybrid path.
And get this, by 2026, it's going to run on 100% sustainable synthetic fuels, showing us a totally different route to high-performance driving.
Okay, let's talk about the car's very bones, because in Formula One, the materials they use are every bit as important as the engine or the wings. This is a sport where every single gram is your absolute enemy.
Every single piece on that car, like the suspension arm, doesn't start as metal or carbon fiber. No. It starts its life as a digital ghost. It gets designed, stressed, and basically tortured thousands of times inside a supercomputer before a single person ever thinks about actually making it.
And only then, after all that virtual testing, does it get to become real. That digital blueprint is transformed into a physical part, like this stunning H-shaped connecting rod made from titanium. It's just a perfect piece of engineering art, sculpted for the most strength with the absolute least amount of weight.
And the palette of materials they get to play with is just extraordinary. The main chassis, that's the driver's survival cell, it's made of this ultra-light, unbelievably strong carbon fiber. The halo, which saves lives, that's titanium. And now they're even pushing into sustainable materials, using things like flax fiber for seats and recycled carbon fiber for less critical components.
So how do they pick what to use where? Well, it is all about trade-offs, and it is pure data. Just look at this analysis for suspension arm. You might think, aluminum is lighter than steel, use that. But not so fast. The data here shows that under the same stress, steel barely deforms, while aluminum bends much more. In this case, stiffness wins over lightness. Every single part on that car goes through this exact kind of data-driven fight.
All right, for our last section, let's dive into something you can't even see, the car's digital brain. Because these days, races aren't just won on the asphalt anymore. A lot of the time, they're won in the cloud.
Let's go back to the brakes for a second, but this time, look at them through a digital lens. It's called brake-by-wire. When the driver hits the pedal, there's no direct physical link. Instead, a sensor just tells the car's brain, the ECU, how hard they're pushing. The ECU then becomes this brilliant conductor, instantly commanding 3 different systems: the brake calipers, the engine braking, and the MGU-K's energy harvesting. This whole balancing act is called brake migration, and it's absolutely crucial for keeping the car stable. And all of these systems are constantly talking to each other, swimming in a massive ocean of data. A single F1 car, with its hundreds of sensors, generates over 1 terabyte of data over just one race weekend. To put that in perspective, that's probably more data than you have on your entire home computer. From one car, in 3 days. And you can really see that evolution right here. On one side, you have the analog age, a legendary driver like Senna trying to make sense of a few printouts. On the other side is today's reality, huge teams of engineers poring over graphs like this, comparing lap data, hunting for thousandths of a second. It's a completely different world, all driven by data. So why does any of this matter outside of a racetrack on a Sunday afternoon? Well, this quote really sums it up perfectly. This technology isn't created in a bubble. The engineering, the new materials, the data analysis, it all eventually trickles down, not just to the car you and I drive, but into completely different fields like aerospace and even medicine. And this brings us to one last big question. You know, as our own road cars become more and more electric, more and more autonomous, what's the future for this? The ultimate, human-driven, high-speed laboratory. What will it need to teach us next?